continue with ordinary differential equation, looking at application of Wronskian. Wronskian is also termed as variation of parameter method. So if you are expected to solve a second order differential equation, y prime prime minus y prime minus 2y is equal to exponential 3x, for example. Now, this question you see, we can use the variation of parameter method. We can use the variation of parameter method, and we can also use the Wronskian method. Wronskian method is a substitute to variation of parameter method. So solution to this using Wronskian, first we solve it when it is homogeneous. This is a non-homogeneous second order differential equation with undetermined coefficients. You can easily get a direct answer. But if we are restricted to use the Wronskian method, Wronskian is minus y1 integral y2, the right hand side function, r function of x differential x over Wronskian y1 y2 plus y2 integral y1 r function of s, the value at the right hand side differential x over Wronskian y1 y2. Take notes. But we solve the first expression, which is the homogeneous part, first. Y prime prime minus y prime minus 2y is equal to 0. This is the homogeneous part of the equation. Now we solve it by using auxiliary equation. Y prime is equal to 5, for example, as an assumption. So we get the auxiliary equation as 5 squared minus 5 minus 2 is equal to 0. And by scissors method of factorization, we can get 5 minus 2 plus 1. This gives us a clear factor to the above expression. And also we have 5 minus 2 into 5 plus 1 is equal to 0. 5 equal to 2 and 5 is equal to minus 1. So if we have this expression, what we do is to get the exponential by complementary function solution, which is exponential minus 1, that is c1 exponential minus x, 1x, plus c2 exponential 2x. This is exponential relationship for the y complementary function solution. And this is the solution to the homogeneous part of the equation from here to here. We now consider the y particular. Y particular is the Wronskian, which is Wronskian expression minus y1 integral y2 r function of x differential x over Wronskian y1 y2 plus y2 integral y1 r function of x differential x divided by Wronskian of y1 comma y2. Take note. So we work out the Wronskian already in this expression from the homogeneous equation where y equal to y complementary is equal to c1 exponential minus x plus c2 exponential 2x. This on its own is the y1 and this is the y2. Take note. They are the first and the second solution in the exponential relationship of the complementary function solution. So we now perform the Wronskian test. The Wronskian test, Wronskian of y1, y2 is Wronskian test for exponent minus x, this value, comma, exponential 2x. And that Wronskian gives us the determinant values of this expression, exponential minus x, exponential 2x. We have to differentiate this to get this other value, which is minus exponential minus x. Differentiate these 2 exponential 2x. Take note. So the determinant will now give us, when this multiplies this, you have 2 exponential x. Exponent minus x plus exponent 2x will give you x. These two multiply. When we are cross multiplying, we'll be having, there is an in-between minus here, and that gives you plus exponential x, and this gives you 3 exponential x. 3 exponential x. Of course, we go straight to this expression, the particular, because we are done with the homogeneous solution. Is the particular part of the solution. So that y particular, using Wronskian methodology, is going to give us minus y1 minus exponential minus s integral y2 exponential 2x multiplied by the right hand side value is equal to exponent 2s. So you use exponent 3s. Is equal to exponential 3s. That's what the value at the right hand side multiplied by differential x over Wronskian, which is 3 exponential x. That was the value you got for Wronskian. Plus y2, which is exponential 2x, integral of y1 minus x multiplied by the right hand side value, what makes the equation to be non-homogeneous, which is exponential 3x differential x over Wronskian, which is 3 exponential x. So when we multiply the top, we have minus exponent minus x. Now over 3, when we bring this 3 out. When you reciprocate exponential x here, we'll be having the integral of exponential 4x differential x. This 3 is already out. We have reciprocated this to get this. So plus exponential 2x. When this comes out to 3 is out at the denominator level. Exponential, now integral exponential, this will give you 2. When it comes up, will give you ordinary exponential function. That is to say, we are having 2 here. When we reciprocate the denominator, we'll be having exponential x differential x. Minus x plus 3s, we are going to get 2x. When this reciprocates, we get x. Then we integrate this further, and this gives us, when this is integrated, you discover that the value at this point is a direct addition. So here we'll be getting minus reciprocal 12 exponential 3x. Why? Because when we integrate this, 1 over 4 will come out this. So by the time this adds together, we are now going to have this expression, which is now the application of this multiplication of exponential minus x with exponential 4x gives you exponential 3x. Because after the integration, you have to multiply with exponential 4s and exponential minus s, which adds together to give you 3s. Then plus exponential 2x plus 1x, automatically you have 3x divided through by 3. Because when this is integrated, it gives you exponent x. Add together, because they are exponential value, you have this expression. So LCM finally gives us 12. And 12 here, we give you 1, you have minus exponential 3x. When 3 goes here, it gives you plus 4 exponential 3x. So because this is 3 into 12 is 4, multiply you have it. So when you sum together, we'll be having 3 exponential 3x over 12. When you subtract this from this. So that at the end of the day, when 3 cancels out, when this cancels out, you have 4. So this gives you 1 over 4 exponential 3x. This will be added as y total is equal to y complementary plus y particular. So y complementary ab initio is c1 exponential minus x plus c2 exponential 2x plus 1 over 4 exponential 3x. Take note that this is the general particular solution for the question. Why? Because the y complementary is added to the y particular. The y particular from Wronskian methodology gave us 1 over 4 exponential 3x. Take note that the Wronskian, which is this W, has to be performed by determinant method, 2 by 2 matrix determinant methodology, to arrive at the value for Wronskian and impute in the general Wronskian y particular expression to get our final answer, which is 1 over 4 exponential 3x. That is the particular component added to the complementary function, the homogeneous solution.